we are here again, hopefully. And yeah, well, let's hope it works properly this time around. Hello. Thank you for coming here. Please click the like button if you want. Let's get back to Nernst equation. Fingers crossed. It doesn't lag. I don't know why it's happening, but I have changed all the settings that were supposed to be changed, so I'm here. Please press the thumbs up because I don't know. Write the Nernst equation for the following reaction. Yeah. So Nernst equation, as we were revising. Hopefully everyone comes here in some time. Everyone who was there, hopefully everyone comes here. So E cell is equal to E naught cell minus RT by NF ln of reaction quotient. So E cell is equal to E naught cell minus 0.059 by N ln Q. So what are the assumptions that we take over there? The assumptions that we take are R is 8.314 joule per mole Kelvin. We assume temperature is 25 degrees Celsius, which means 298 Kelvin. We assume that Faraday's constant when taken in SI units is 96500 coulombs. And once these values are filled in, we get E cell is equal to E naught cell minus 0.059 by N into ln of, sorry, not ln, we take log of Q over here. Log of Q. So we are also assuming, that ln Q is equal to 2.303 times log of Q. Okay. So that is what we are doing in this particular equation. Now for the chemical equation that is mentioned, do you realize what is Q? Q would be zinc 2 positives concentration divided by copper 2 positives concentration. Yeah. It will be zinc 2 positives concentration divided by copper 2 positives concentration. Okay. Now, what we ignore over here is these pure solids. Yeah. For pure solids and pure liquids, we do not take their contribution inside the reaction quotient. What we are assuming over here is that copper solids contribution is 1. What we are assuming over here is zinc solids contribution is 1. Okay? Because technically speaking, these values don't really change. So these values are as good as constant. So let's take the constant as 1 over here. Okay? So Q is equal to zinc 2 positive by copper 2 positive. This is the reaction quotient for this particular cell. So how can we write it over here? We can write E cell is equal to E naught cell minus 0.059 by N into log of concentration of zinc 2 positive divided by concentration of copper 2 positive. Products upon reactants. Okay. Now, when we do this, if I increase the value of zinc, the negative thing increases. Do you understand? Because there is a minus sign over here. If I increase zinc, the overall thing becomes more negative. So if zinc goes up, can I say that the E cell goes down? And similarly, if copper goes up, I can say that the E cell goes up, because this entire thing is mixed with a negative sign. So if you make this more, negative sign becomes more. Okay, so copper 2 positive ions are increased, E cell will increase. Zinc 2 positive ion increase, E cell will decrease. Simple application of the Nernst equation. Now, how do we calculate this N? Yeah, some of you are having this doubt. Sir, how do we calculate this N? The N is the number of electrons involved in the redox reaction. So once the redox reaction is balanced, as it is over here, see the redox reaction is balanced. In the oxidation process, how many electrons are involved? 2 electrons. So this is N. You calculate N either from the oxidation process or from reduction process. Same thing. Even if you do it, this is also 2 electron process. Oxidation process loses 2 electrons, reduction process gains 2 electrons. Basically, N over here will be equal to 2. Okay. Now, Lucy is asking how to remember the electrochemical series. I don't think anyone's going to ask you memory-based questions from electrochemical series. They will give you the values wherever necessary. They will give you the reduction potentials where they are necessary. Okay. So, look at this 3-mark question with a choice. So, over here they are asking you to calculate delta G and equilibrium constant. They have given some values over here. The other question says calculate EMF for this particular cell via the Nernst equation. So, let's do both the questions one by one. Let's first use the Nernst equation. Yeah. Let's do the Nernst equation first and then we'll do the other one because we've just revised the Nernst equation. So, let's see. Calculate the EMF of the following cell at 298 Kelvin. Fe solid, Fe2 positive, H positive, H2, whatever. Yeah. Fe2 positive, H positive. Okay. So, how do we write this particular equation? How do we write this equation? The equation can be written in this particular manner, that your Fe solid is getting oxidized to Fe2 positive. This is the reduction part of the equation. Now, what is the, this is the oxidation part of the equation. What is the reduction part going to look like? What is getting reduced over here? Essentially, my H positive is getting reduced to H2. Yeah. My H positive is getting reduced to H2. So now how do I balance this reaction, people? How am I supposed to balance this reaction? To balance this reaction, I should put a 2 over here. I should put a 2 over here. So now let us try to understand if this reaction is balanced or not. This is a 2 electron process. Yes. This one, H positive, that is +1 oxidation state going to 0 oxidation state. This is a 1 electron process for 1 H atom. It's a 1 electron process for a single hydrogen atom. So for 2 hydrogen atoms, this is a 2 electron process. 2 electrons in oxidation, 2 electrons in reduction. Electrons are also balanced. So for this case, N is equal to 2. How will we write the Nernst equation now? The Nernst equation will be written as E0 minus 0.059 by N, which is 2, into log of, what is the reaction quotient? What is the reaction quotient over here? Now the reaction quotient will be equal to pressure of hydrogen gas in atm into concentration of Fe2 positive divided by the concentration of H positive squared. Concentration of H positive squared. And do we take the contribution of this? No, because this is a pure solid. Okay. The contribution is, that is a pure solid. So this is the reaction quotient. So that's what you have to fill over here. So what is the pressure of H2 given as? 1 bar pressure. Okay, nice. What is the iron's concentration given as? 10 to the power minus 3 molar. Divide by, what is the H positive's concentration? 10 to the power minus 2, but this is squared. Fill the values, people, you'll get the answer. With Arshana saying, are the equations for batteries required? Please say. Generally, they don't ask you those equations in board examinations, but since this year physics has been difficult, they might ask. 1 or 2 mark, they might ask the equation of batteries also. Okay. So, Just giving you an idea. If you can remember, then fine. If you can't remember, then leave that question. Simple as that. So people, what will be the answer? E naught cell is given 0.44 minus 0.059 upon 2 into log of, this is what? Log 10 only, no? Yeah, if I'm not wrong, that's all you have to do. 0.44 minus 0.059 by 2. Do the calculation, simple. Just the n value is 2. We've calculated it over here. Please rewind and see if you missed that part. Peaky, yes, they will cut marks if you don't write the units. If you don't write the units of the final answer especially, they will cut the marks. So people, this is how we apply the Nernst equation over here. Pressure has to be taken in bars or ATM. ATM bar both have the same value approximately. So pressure has to be taken in ATMs or bar, and the concentration has to be taken in molarity, moles per liter. Cool. Let's do this one. Calculate delta G and log Kc for the following reaction. In hydrogen electron in the cathode side, after H positive, should we write H2 part in the cell? H2. Achha. So basically you're saying, should we start from H positive or should we start from H2? Is that what you're saying? Basically you do a reduction process. Okay, so reduction process basically means your H positive is going towards molecule H2. Alright. So for reduction potentials, you always write the reduction reaction. Anyway, if there's a different doubt, then please elaborate it a little better. Calculate the delta G and log Kc for the following reaction. People, what is the relationship between delta G and K equilibrium? Delta G is equal to delta G naught minus RT ln Q. This is where the Nernst equation comes from. When you take this equation and use the other equation that says delta G is equal to minus NFE, when you combine those equations, that is where you get Nernst equation from. So this is the basic idea that we have. Now, at equilibrium, I'm sure you remember that delta G is supposed to be 0. At equilibrium, delta G is supposed to be 0. So I can write that delta G naught is equal to RT ln K equilibrium. Now tell me if this equation is correct or not. Tell me if this equation is correct or not. People, those of you who are actually attending the class, can you tell whether this equation is correct or not? I will reduce the slow mode so that you guys can answer. Tell me, is this correct or no? Yeah. What do you think? Minus sign is correct or no? Think about the minus sign. Is this correct via sign? People, please check if the sign is correct or not. This is incorrect. This is incorrect, okay? This equation is supposed to be delta G equal to delta G naught plus RT ln Q. So delta G naught is equal to minus RT ln K equilibrium. Okay, that minus sign. Fine. So how do we derive the Nernst equation, by the way? When we have this delta G is equal to delta G naught plus RT ln Q, and we combine this with the equation delta G equal to minus NFE. When we combine these two equations, that is when we get the Nernst equation. Yeah. So this is where the sign comes from in the Nernst equation. Anyway, delta G naught is equal to minus RT ln K equilibrium. So what does this say? This gives me the E naught cell. This gives me some random value of the Faraday's constant. Okay, fine. So this can be written as minus NF E naught cell. That's what I have. So I can say that NF E naught cell is equal to RT ln K equilibrium. So now calculate the N, please. 2. N is 2. Faraday's constant is given as 96500 coulombs. E naught cell is given as 1.05 volts. R, if nothing is given, we'll assume R is 8.314 joule per mole Kelvin. Temperature, if nothing is given, we will assume it is 298 Kelvin. And K is what we'll calculate. So just plug in all the values, you calculate K. And anyway, log is asked. Okay? Anyway, log Kc is asked. So you can write it simply like this. Log K is equal to, I can simplify this equation in a slightly different manner. We will write E naught cell is equal to RT by NF into 2.303 log of K. So this entire value we already know is 0.059. So we can write 1.05 by 0.059 is equal to log of K. Yeah, this is coming out as log of K. So now if you have log K, just put the value and calculate delta G naught also. So remaining part you can do. Mithilesh, yeah, we have to put N also over here. Thank you for the correction. We will put N over here as 2. Good stuff. Tarun, so there is a difference between delta G and delta G naught. This is standard enthalpy change of, standard Gibbs energy change of the reaction. This is calculated at certain conditions, but this is the actual Gibbs energy change of the reaction. So this is the standard fixed value for any reaction which we calculate. This is the actual value which is 0 at equilibrium. Okay. Fine. Sorry people, that lag thing has broken my flow of the class. This should be the answer. 2.1 divided by 0.059. Prefix, so when nothing is given, we assume temperature to be 298 Kelvin. When nothing is given, we assume room temperature. Okay, so this is what the answer should come out to be for log K. All right, let's move to the next part, this one. The molar conductivities of NH4 positive and Cl negative are that and that respectively. What molar conductivities are those? Those are usually your limiting molar conductivities. Yeah. When ions have been mentioned separately, those are usually limiting molar conductivities. So I can say lambda infinity for NH4 positive is given as 73.8 and lambda infinity for Cl negative is given as 76.2. Now it is said the conductivity of 0.1 molar NH4Cl is 1.29 into 10 to the power minus 2. Calculate the molar conductivity and degree of dissociation. One by one, we will have to do this. Okay, chalo. So people, first of all, what is going to be the lambda infinity for NH4Cl? Will be the addition of these two numbers. Can you add these two numbers for me, please? First of all, give me the answer of this in the chat. Ramamurthy, we've already done that. This is an extension of the previous class that was already going on since 1 p.m. So if you want to know that part, Ramamurthy, the dependence of molar conductivity with concentration, I explained that half an hour explanation I gave for it. Please go to the previous live session and watch it. Yeah. How much is this coming out to be? 150. Good. So 150 is the value for lambda infinity of NH4Cl. Now, my dear friends, over here it says for 0.1 molar NH4Cl, the conductivity is equal to 1.29 into 10 to the power minus 2. What will be the molar conductivity of this NH4Cl? See, over here you can either use formula or you can also use logic. You can use formula or you can use logic. See, this much is given to us. 0.1 molar NH4Cl conductivity is this much. Yeah, and this is given in centimeter inverse. Now understand the logic. You can directly apply a formula also, I don't mind that. But this basically says that 0.1 mole of NH4Cl, yeah, is present in 10 to the power 3 centimeter cube of solution. This is what the statement means, the molarity statement. Do you understand? This is what the statement for molarity means, right? Just a second. So how will I calculate the molar conductivity? How will I calculate the molar conductivity? Logically explaining this idea to you. What I want is, I want 1 mole. So 1 mole will be there in 10 liters of solution has 1 mole. So I will have to take the value of this solution and multiply it to take the according volume over here. Yeah. I will have to multiply it to take the according volume over here. So this one, yeah, this value is for 1 cubic centimeter, but I need the value for 10 to the power 4 cubic centimeter. This value they've given is for 1 cubic centimeter. I need the value for 10 to the power 4 cubic centimeter. So lambda molar will be equal to 1.29 into 10 to the power minus 2 into 10 to the power 4, which is equal to 129. You did by formula, perfect. Do you understand the logic by which we did? Just giving you a different perspective, because formula application is very stupid, right? You know something, you put the values there, okay, it works, you will get marks. But understand from the perspective of a scientist as well. The value given over here is for 1 cubic centimeter block. I need to calculate value for 10 liters because 10 liters contains 1 mole of the substance. So 10 liter can be written as 10 to the power 4 cubic centimeters. So this value is for 1 cubic centimeter. Calculate the value for 10 to the power 4 centimeter, comes out to be 129. Better perspective. Okay, better perspective given to you. Otherwise, if you want to know formula says that lambda molar is equal to your lambda divided by concentration into 1 1000. That's the formula. Okay, so that is the formula over there, but this is a slightly smarter method. So molar conductance is here, limiting molar conductance is here. My dear friends, you should remember that degree of dissociation is defined as molar conductance upon limiting molar conductance. Okay, this is how we define degree of dissociation. So what is degree of dissociation basically? The particles that have reacted upon initial number of particles. So that can be thought of as molar conductivity upon limiting molar conductivity. So if we can keep this in our minds, this idea becomes very simple. Yeah? Degree of dissociation will be equal to 129 by 150. All right. Okay. So now, just so that I deter students from doing random jazz in the chat box, once again, we're going to increase the slow mode. All right. Fine. So, when we add these limiting molar conductivities with each other, what is that law called, people? What is the law where we add limiting molar conductivities of individual components to get the final molar conductivity? That law is known as the Kohlrausch law of independent migration of ions. Yeah. So the law that we are talking about is known as Kohlrausch law of independent migration of ions. Using Kohlrausch law of independent migration of ions, it is possible to calculate lambda infinity for any electrolyte from the lambda infinity of individual ions. Moreover, for weak electrolytes acetic acid, it is possible to determine the value of its dissociation constant once we know the lambda infinity and lambda at any given concentration C. Yeah. So that is how we figure out the limiting molar conductivities. So these are the values of limiting molar conductivities that are given. So if you want to calculate the limiting molar conductivity for NaOH, simply add these two values. If you want to figure out limiting molar conductivity for HCl, simply add these two values. Okay, so this is how you can calculate the value of limiting molar conductivities. On the basis of the above observations, he enunciated Kohlrausch law of independent migration of ions. The law states that limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and cation of the electrolyte. Thus, example is given. Okay, so if I show you that question, this one, now you know the part of the second, you know the answer of the second part. Suggest a way to obtain this value. Also state the related law, if any. So it says that for strong electrolyte, you can plot a graph. Okay, great. But what about the weak electrolyte? So for weak electrolyte, the law that we will use over here will be the Kohlrausch law. If we can use the Kohlrausch law, for weak electrolytes, we can obtain the value of limiting molar conductivity, because from the graph we can't do it, because the graph is too unpredictable for weak electrolytes. So we'll use the Kohlrausch law of independent migration of ions to calculate the limiting molar conductivity of weak electrolytes. Cool. So such values will be given to you if they want you to calculate the limiting molar conductivity like we have done in this particular question. Okay. All right. Coolio. Look at this. Electrolysis. Now this is a memory based question, by the way. This is a memory based question. When we electrolyze brine, what do we mean by brine? Yeah, Brine basically means solution of NaCl in water. So when we have NaCl in water, there are multiple equations that can happen. Yeah, there are multiple things that can happen. What are the multiple things that can happen? These are the multiple things that can happen. Yeah. What's the first reaction? The first reaction is essentially the oxidation of chlorine. So this is the oxidation of chlorine. Then what's the next reaction? This is also the oxidation of OH negative. And then the last two reactions that are given over here. So these can happen on the anode. The anode can give you these two oxidation reactions, and these are the possible reduction reactions that can happen. So this is the reduction of sodium positive, and this is the reduction of H positive. So out of the four, only one reduction will happen and only one oxidation will happen. Now, which oxidation happens and which reduction happens, that depends on your reduction potential. That depends on your Terror 777. I will give you another example after this, okay? Please remind me after we've done the stipulated questions. I will give you an example of that. Okay, Sashwini, that is what we will understand over here in this question. Fine. So let's go to our good old book to study a little bit about the electrolysis part, because this is generally something that we ignore because it's given at the end of the chapter. So that's why we need to focus a little bit on electrolysis. Look at what is happening over here. Look at what is happening in the electrolysis of brine solution. Let's read this paragraph properly with patience. If we use melted NaCl, molten NaCl means we've taken NaCl, we've taken it to a very high temperature and melted it. There is no water here. Molten NaCl means there is no water. So the products of electrolysis will be perfect sodium, metal and chlorine gas, because there is only one cation which will get reduced. There is only one anion which will get oxidized. But now when we do this in water, there is competition. Look at the competition. You can have sodium's reduction or you can have hydrogen's reduction. Sodium does not want to get reduced. Sodium says if I want to get reduced, I have to absorb 2.7 volts. You have to give it 2.7 volts for reduction. But hydrogen is like, I will reduce, no problem. 0 voltage, not required. Then when we look at the reactions for chloride ions oxidation versus water's oxidation, chloride ions oxidation is better than water's oxidation, yes? It's easier to oxidize chloride ions. It is not as easy to oxidize water. Higher voltage means easier process. Higher voltage means more spontaneous process, as we understood in that question where that lag happened. Yeah. So, the reaction at anode with lower value of E0 is preferred, and therefore water should get oxidized in preference to chloride. However, on account of over potential of oxygen, reaction 2.36 is preferred. Okay. On account of over potential, this is what is preferred. So, what are the reactions that will happen? Have a look. Please have a look at the reaction. On cathode, water will get reduced. At the anode, chloride will get oxidized. This is memory based now. Which one is easy, which one is not easy, that comes after doing an experiment. This is something that we have to remember. So when we electrolyze brine, your cathode does reduction of water and your anode does oxidation of chloride ion. Okay. So what are the processes that are happening over here? we will have, what are the processes that will happen over here? Chloride will be oxidized and reduction will happen on the other side. Sodium will not happen. H positive will get reduced on the other side because that is the easier process. Done. So this is just a memory based question from electrochemistry, people. Okay. You can read a little more about electrolysis. Very beautiful ideas given over here. Competing reactions, and have a look. Moreover, some electrochemical processes are feasible but very slow. So at lower voltages, these do not seem to take place and extra voltage has to be provided. So that is called overpotential. Let me explain this to you in a slightly more eloquent manner. My dear friends, if I ask you a question which says, what do we mean by spontaneity? What do we mean by the word spontaneous? Can you tell me? Can you tell me what do we mean by the word spontaneous? Ashish, we've done that in the inorganic chemistry class day before yesterday. Please go and watch that. So if I say spontaneous, what does it mean? Spontaneous simply means that it happens and that's it. It happens. A spontaneous process is something that happens. Sometimes it just happens on its own. Sometimes we need to push start it and then it keeps happening. So a process that happens on its own is spontaneous. Sometimes we have to push start the process. Okay. So now, my dear friends, spontaneous process can be slow. It can also be fast. It can be slow. It can be fast. Okay. It can be slow, but it can be a fast process also. Can you give me an example of a slow spontaneous process? The most common example that we study about is rusting of iron. Yes, the slow spontaneous process, rusting of iron, it takes years to happen. It takes years to happen. Fast spontaneous process. What would be a fast spontaneous process? Once I ignite paper, it keeps burning in oxygen. Yeah. So there are lots of examples of spontaneous process. Once we start the reaction, it keeps happening. So burn paper. Cool. So these ideas, spontaneity is not related to speed. Spontaneity is not related to speed. So people, what is overpotential? During electrochemistry, if there is a reaction that is spontaneous, it might be a very slow reaction. It might be a very slow reaction. So in that overpotential case, the oxidation of water is very slow. Oxidation of water can happen, but it is a very slow process. That is why chlorine's oxidation happens over there. Chloride ion gets oxidized, water doesn't get oxidized because water's oxidation is a very slow process. Okay, got the idea? So that is the meaning of overpotential, that if we want that slow process to happen faster, we have to give it extra voltage. Alright, we have to give it extra voltage. Cool. So now, people, the practice part of this session is over. For chemical kinetics and for solutions and colligative properties, watch part 1, please. Watch part 1 for those two chapters. This is part 2. Why did we do part 2 today only? Because there was a problem with the YouTube stream. Okay. Shrudeep, yes, in fact it is. In fact, you are right. Okay. So now, if you've got any doubts, you can ask me. Hopefully, these are relevant doubts. Irrelevant doubts, I will not address, of course. So, turning the slow mode to a lower value, hopefully. You guys ask me relevant doubts. If you've missed any part of the class, please rewind and watch it again. Please use technology. Tell me, people, if you've got any doubts. All the best for your board examinations, by the way. Good luck. And I'm sure you'll be able to do well now that you understand the ideas. Shriram is asking, will the paper be tougher? I don't know, man. I did not set the paper. So I can't say anything. Adi, yeah, 50 will be very easy. Sumit is saying how to calculate equivalent weight. Equivalent weight is calculated by molar weight upon equivalent factor. So what is equivalent factor? For acids and bases, equivalent factor is the number of H positives the acid can furnish or the number of OH negatives that the base can furnish. And for the redox reactions, the number of electrons involved in that oxidation or reduction is equal to your equivalent factor. So for example, if you look at this particular process, this is a 5 electron process because you're going from a +7 oxidation state to a +2 oxidation state. So equivalent weight of KMnO4 in this process will be equal to molar weight of KMnO4 divided by 5. Okay, yes, molar conductivity I will do. Scarzi is saying, why did bohr take? Because it was the simplest available species. It doesn't have neutrons, so it is easier to do the calculations without worrying too much about the interaction of multiple electrons and multiple protons. Shankara, GOC will do after your boards are over. Sums related to Faraday's law, Nitla Darshani, those are pretty easy because all you need to do is just see how many electrons are involved in creation of one final particle. So just try them on your own. I mean, I'm sure you will figure that out. What is valence bond theory actually explaining? It does not explain anything. It just predicts the shapes of molecules and hybridization of molecules by looking at their magnetic nature. So that's the problem with valence bond theory. It does not predict anything. Yeah, animal gaming group, please rewind and watch that part again. Bhuvana, so E naught of cell is at standard conditions when all the electrolytes are 1 molar concentration, the pressure is 1 atm, the temperature is 298 Kelvin, etc. So when everything is standard, that is when we get E naught. E of cell is at any time. The concentration could be 20 molar, 3 molar, 50 molar, etc. Temperature could be anything, pressure could be anything. So E naught, whenever we say naught, it's a standard value. It's defined at standard conditions, standard concentrations. Okay. Lucy, I'll show you the exact hydrogen electrode picture. Okay. Batteries are tough to study. Yes, Dev, I agree. Deva, bro, I agree. Manish, because cathode is wherever you have reduction, anode is wherever you have oxidation. So when you have a galvanic cell, things are happening on their own. When you have electrolytic cell, it becomes opposite. So always think of cathode and anode in terms of oxidation and reduction. Negative and positive will follow. Okay, so now that logical method for molar conductivity, for that let me bring out a question from the NCERT itself. Yeah, I think there is a better question from which I can explain that idea to you. Molar conductivity. Let me see where it is. Yeah, perhaps this one. Okay. So what's given over here? Resistance of a conductivity cell, that much is 100 ohms. If the resistance of the same cell when filled with 0.02 mole per liter KCl solution is 520 ohms, calculate the conductivity and molar conductivity of whatever. Okay. First, let's calculate the conductivity. Yeah. So can you figure out how to calculate conductivity? Can you figure out how to calculate conductivity? Same idea. 1 by R is equal to 1 by rho into 1 upon L by A. Yeah. So basically it says resistance of conductivity cell filled with 0.1 mole per liter KCl solution is 100 ohms. So that gives me conductance of this particular case. The other part gives me conductance of the other case. So that will give me the cell constant basically. Yeah. Yes or no? Because the conductivity cell is the same. So basically your cell constant will be the same for both the cases. Right? So because the cell constant will be the same, can you calculate the conductivity? Try that part. Okay. Now focusing on the second part, it says the conductivity of 0.1 mole per liter KCl solution is 1.29 whatever. So look at this, Jazz. 0.1 mole per liter KCl. What does this imply? For whoever wants to understand that logical thing, please pay attention. Can I say this means I have 0.1 mole in 1 liter of solution? Can I multiply by 10 on both sides? Can I say I have 1 mole in 10 liter of solution? Now 10 liters of solution can be written as 10 to the power 4 cubic centimeters. Yes, because we know 1 liter is equal to 1000 cubic centimeters. But at the same time, do you remember that 1 liter can be written as 10 to the power minus 3 cubic meters? Do we understand that part or not? Is that part making sense to you? If I'm wrong, please correct me. Sometimes I do silly mistakes in mathematics. One cubic centimeter is equal to, sorry, you can write 1 cubic meter is equal to 10 to the power 6 cubic centimeters. This one you understand? 100 into 100 into 100. So do you get this? Does this make sense to you? 1 liter is 1000 cubic centimeters. So 1 liter is basically 10 to the power minus 3 cubic meters. Okay, fine. So this solution, if I need 1 mole of iron, if I need 1 mole of the ions in this solution, I will need 10 to the power minus 2 cubic meters. Okay. Now look at the value that is given over here. This value is 1.29 Siemens per meter for a 1 meter cube block. Why 1 meter cube block? Because the unit is meters. So this value for conductivity that is given is the conductance for that block that we had written. That small block that we had written for calculating conductance conductivity. So when that block is 1 cubic meter, this is the conductance of the solution. But I want the conductance of the solution when the block is 10 to the power minus 2 cubic meters. So let's multiply with 10 to the power minus 2 on both sides. 1.29 into 10 to the power minus 2 for a 10 to the power minus 2 cubic meter block. So this is the value of molar conductivity. Yeah. So those of you who wanted to know the logical method without understanding the formula, do you understand now? How this logical method is better because you don't have to remember different formula for meters or different formula for centimeters. You simply think what is the volume required for taking 1 mole of substance. You calculate that by the concentration and then figure out the value that is given, that is going to be for 1 unit volume. Now that 1 unit volume could be meter cube, could be centimeter cube. Yeah, that's the idea. Adventure boy, bro, what part did you not understand? And have you revised electrochemistry on your own before this class? Because this is supposed to be a revision class. Yeah. So if you don't know electrochemistry, then you won't be able to understand this idea at all. Okay. Loons, bro, you are not converting mole per liter to meter cube. You are basically looking at this definition. This definition says I have 0.1 mole in 1 liter of solution. So by that definition, I can say I have 1 mole in 10 liter solution. What is 10 liter? 10 liter is equal to 10 to the power minus 2 cubic meters. Okay. Lucy, always think in terms of oxidation and reduction. Don't think in terms of positive and negative. That will help you define anode and cathode better. All right. Good stuff. This is why I kept physical chemistry at the end, because some concepts are a little tricky to explain, especially when you're not using formula. I could have gone formula, and you'll be like, okay. That's not the point here. Fine. So now, homework for you is to read and revise the NCERT as much as you can, as best as you can. I will take your leave right now because tomorrow you have the examination. So all the very, very best for your board examinations. And hopefully you will see me soon after your board exams for a class of j, practicing j questions. And that will be a lot more fun because I love solving the difficult questions. Yeah. Acha, collision theory. Okay. Nitila, I'll discuss collision theory because you were asking about it for a long time. So what happens in collision theory is, can you tell me when will a chemical reaction happen? And people who want to leave the class can leave, okay? This is just extra information for the interested students. If you want to leave, that's absolutely fine. When will a chemical reaction occur? Sorry. A chemical reaction will occur under certain conditions. First of all, when two molecules collide. And I'm assuming it's a bimolecular reaction. So we have molecule A plus molecule B going towards a product P. So assuming it's a bimolecular reaction, when these two molecules collide, first of all that, then the second thing is that the two molecules should collide with enough energy. First of all, the collision should happen, but collision should happen with enough energy. Yeah. Imagine this is A, this is B. First, the collision should happen. But if the collision happens very slow, there's no reaction. It should happen with a certain amount of energy. Then these will stick together. That's the second point. The third point over here is, what if they collide like this? This will not give me any reaction. What if they collide like this? No reaction. What if they collide like this? No reaction. So out of the infinite collisions that are possible, there is only one collision that makes sense. So out of all the collisions, they should collide in the correct orientation. Now we have to convert this into mathematics. This is what your rate constant is. Rate constant for any reaction basically contains the information about collisions, what is the energy of the collision, and what is the orientation of the collision. So if the rate constant is higher, these values are basically higher. So what does your rate equation look like? Rate equation basically looks like K into amount of A into amount of B. Yeah. So amount of A and amount of B is very simple to figure out. Yeah. More A, more B, faster will be the collision. Okay, that part is taken over here. Faster will be the reaction. More A, more B, faster reaction. That part is taken care of. K includes information of all these 3 points. Now, how do we convert them to mathematics? Do you realize this has already been converted to mathematics? E to the power minus EA by RT. That's your Arrhenius equations exponential part that comes from the Maxwell-Boltzmann distribution. Right? Perfect. Now, you want two molecules collision and their collision in perfect orientation. So, my dear friends, the collision of two molecules, you can call this collision frequency. How often are they colliding? This is known as collision frequency and can be represented by this letter Z. That more frequency, more is the number Z. Okay, and collide in the correct orientation. So there will be some probability of correct collision, right? Out of 100 collisions, let's say 2 collisions are fine for reaction. So there will be some probability of collision. We will represent this with the probability P. This is the probability of correct collision. So when we combine these 3 factors, I can say that the rate constant should be equal to probability of correct collision into the number of collisions into the collisions that have enough energy minus EA by RT. So this entire thing clubbed together can be written as the Arrhenius constant A. So Arrhenius, in fact derived this idea experimentally. So Arrhenius theory came first and then came the collision theory. And collision theory coincides perfectly with the Arrhenius theory. So Arrhenius did some experiments, figured out some values and gave this. Smart scientist. Raga Sudan is saying, I haven't studied a single thing, what to do? Take boards next year, bro. I hope that was sarcasm. Pranish is saying, why are we taking probability factor? Because all the collisions are not useful for us, right? Only some collisions are useful. So probability of some collisions over all collisions will be a smaller value. Okay. Ragasudan, bro, see, ideally you should take the exam again next time. This time all you can do is just open the NCERT and read some pages. Will this session be enough to score 100% in physical chemistry? Lunel, I will not say 100% because you also need to do some practice. This was a revision class. So revision one day before the examination does not mean you'll get 100%. That depends on your efforts. Lucy, thank you so much. Okay, what else? Osmosis. What do you want to know about osmosis, people? The one who are here about osmosis. This is the membrane. Okay. And over here we have 100% water. On the left hand side, let's say we have 90% water and 10% salt. Where will the water move? Where will the water move? From left to right or from right to left? Water is more over here, water is less over here. So water will move from where it is more to where it is less. Okay. Water moves from right to left. Simple. This is osmosis. This membrane only allows water to move. This membrane does not allow anything else to move. This membrane does not allow salts, ions, etc. to move. This membrane allows only water to move. So water is more, water is less, more towards left. More towards less. Right to left. Yeah. So in schools, they teach you in a very complicated and confusing manner. They say that water will move from high concentration of solute to low concentration of solute, and that kills your brain. What? Think about water itself. More water to less water. Simple. Okay. So no need to complicate this idea even further. More water to less water. That's all. So the thing about our body and the cells, that they also work on osmosis. Now the thing with osmosis is that in our body the cell membranes are even more intelligent. So the cell membranes allow sodium from outside to inside, potassium from inside to outside, something like that. Yeah. So that's how the osmosis works in our body. The membranes are intelligent. They will allow something from here to here. They will allow something else from here to here. So slightly more intelligent osmosis. Yeah. Now what is osmotic pressure? If water is moving from right to left, if I want the water to stop moving, I will have to apply some pressure over here. That pressure will push the water on the right hand side. So the amount of pressure I use over here to stop the water from moving is called osmotic pressure. Coolio. Okay, so I've explained all these ideas as well. All the very best for tomorrow's examination. What else, people? Shall we finish the session? Cool. Muhammad Arshad, did you explain molar conductivity? See, the more idea of molar conductivity I've explained in part 1, so please go and watch that part. You will understand it much, much better. Okay. Mala, that is the universal gas constant, R. Alright, so people, that's it from my side. Thank you so much for joining in. I hope you enjoyed the session, and we will see each other very, very soon. Those of you who are requesting for beatboxing, that's enough for now. I will see you guys later in some session. Thank you so much. Bye bye. Take care. All the best.